Welcome back, y'all. This is going to be our second video in our chemical bonding series, and in this one we're going to talk about the characteristics of ionic and covalent bonds, as well as intermolecular forces. So the reason that elements are going to form bonds is because it's going to allow them to lower their energy. And lower energy means more stable in the chemical world. What type of bond the elements are going to make is going to be governed by electronegativity. So we talked about that, and we know that it increases as you move up a group and as you move to the right on the periodic table. So your nonmetals are very electronegative, your metals are not very electronegative. So if we look at the difference in electronegativity between whichever two elements we're trying to bond, we can predict what kind of bond it's going to make based on that difference. If the electronegativity difference is basically zero, then you're going to have a purely covalent bond, which means that the two elements are going to share electrons so that each one fills octet rule. If it's kind of in the middle ground, so somewhere between 0.4 and 1.8, if we're looking at the Pauling scale, then what you're going to end up with is a polar covalent bond, meaning that one of the elements is an electron hog, and you're going to see a partial positive and negative charge on the two atoms participating in the bond. And then if there's a large difference in electronegativity, so something bigger than 1.8, it's an ionic bond. One element is going to give up its valence electrons to the other one, and they're both going to ionize and have charges. So if we consider the electronegativities of the different elements, nonmetals have very similar electronegativities. So they are going to form covalent bonds whenever they are trying to attract to each other. Also, metalloids and nonmetals will form covalent bonds. And so we refer to covalent compounds as molecules. Right. And again, each element in the bond is trying to achieve a full octet, with the major exceptions being hydrogen, which only needs 2 electrons to be full, quote unquote, because it only has that one s orbital that it can fill electrons in, so it can only hold 2 electrons. And boron, notably, will only have 6 electrons total in bonds, because it only has 3 electrons to itself to participate in a bond. So it is with the covalent compounds that you're going to see these intermolecular forces that we're going to talk about in a little bit here. But the general properties of a covalent compound is that they have a low boiling and melting point, which is why most of them are liquids or gases at room temperature. They also, when compounds solidify, remember that the atoms are very closely packed together. Well, that can be either in a rigid crystal structure, or it could be in an amorphous structure, meaning not very geometrically arranged. Covalent compounds fall into that second category. When they solidify, they don't form a regular crystal and are very brittle and easy to break. Covalent compounds will be non-electrolytes. They do not conduct electricity in a solution. And they are also poor conductors of heat and electricity. Now, we can draw Lewis structures to illustrate the formation of the bonds in ionic and covalent compounds. With covalent compounds, I find it useful to use what's called the Fvsbl method, which is the full valence shared bond loan. So if we look at a given Lewis structure for a covalent compound, and we count up, number one, how many electrons does each atom in the compound need to be full? And then we add up how many total valence electrons do all the atoms have. If we subtract those two numbers, that tells me how many the atoms are going to share between them so that everyone can achieve octet. And if we divide that number by 2, we get the number of bonds that they're going to have. And then whatever number is left over between the amount to be full and the number that are shared are what we call lone electrons, where they will exist in pairs on one of the atoms that has not filled octet. So if we use hydrogen as an example, the rule is for covalent compounds is the least electronegative element in the bond is the center part of the molecule, unless carbon is there, in which case carbon is always the center molecule or center part of the molecule, and hydrogen never is. So if we look at water, which is H2O, oxygen has to go in the middle because hydrogen can't. If I add up the total number of valence, or how many they need to be full, oxygen needs 8, and each hydrogen needs 2. So 8 and 2 and 2 is 12. All right, and where is my... I thought I had a tool in here somewhere, so I could draw on this. Nope, that's my pointer. Nope, don't want that either. Go away. Oh, come on, go away. Aha. There it is. This is what I want. Here's my thing. All right, so we have, to be full, we have 12. Ooh, this is really bad. Then the number of valence is going to be, oxygen has 6, and hydrogen each has 1, so that's 8. Really bad drawing tool. So if I subtract those, I'm going to get 4. And if I divide that by 2, I'm going to get 2. So it's going to share 4 electrons, which means it's going to form 2 bonds. And then that means there will be if I subtract the 4 from the total valence of 8, I'm going to have 4 lone. All right. So we put the oxygen in the middle, and you can either draw electrons in between the atoms that are sharing, or you can use lines to represent. So each line represents 2 shared valence electrons. So we would draw lines from the middle atom to each of the outer atoms. Has to be at least 1 bond each for them to be attached. So there's my 2 bonds. And then these 4 lone electrons, for water, they can't go on the hydrogens. So hydrogen can only, because hydrogen can only have 2 electrons, or 2 shared electrons total. So the other 4 go on the oxygen in a pair to fill oxygen's octet, because that would give, each line counts as 2 and counts for both of the atoms attached to it. That would give oxygen 2, 4, 6, 8, and each hydrogen has 2, and so that's full, and we're good with that. Okay. Now, so that's covalent bonding and Lewis structures. Now, with ionic bonding, there's a large electronegativity difference between the atoms in the bond. So that means that one element is going to give up electrons and the other is going to gain. And so with something like sodium chloride, for example, which is salt, the sodium is not very electronegative and the chlorine is very electronegative. So the sodium will, and also we should mention ionization energy. Sodium has a low ionization energy and chlorine has a high one, which means that the sodium is going to be pretty simple to remove this electron off of the sodium, and then the chlorine is going to readily accept it so it can fill its octet. And so what we end up with is a positively charged sodium ion and a negatively charged chlorine ion. And these are very strong opposite charges, and we know that opposite charges attract. So the 2 atoms in the bond are going to attract together and make this ionic bond. And then with ionic compounds, they do form what's called a crystal lattice structure. So you see that you will have each cation surrounded by anions and vice versa. so that all the charges are neutralized, and it's a very strong, rigid structure. So to draw the Lewis structure for ionic compounds, you have to show how each atom is going to gain or lose its electrons so that you end up with a neutral compound. And it's not necessarily going to be one cation donates an electron to one anion and you have a 1-to-1 ratio. So if we look at calcium chloride, for example, calcium needs to remove 2 electrons, but each chlorine can only accept 1. So it would take 2 chlorine atoms to take both of these electrons away from the calcium. So we end up with a calcium with a +2 charge and 2 chloride ions with a -1 charge, which is why the formula for calcium chloride is CaCl2. Remember, the subscripts tell me how many atoms of the element that's attached to it we have. And if there's not a subscript, then we assume that that number is 1. So because ionic bonding is very, very strong and very, very organized, we see that ionic compounds have very high boiling and melting points, which means they're usually solid at room temperature and form that rigid crystal lattice. The ones that are soluble in water, which we call electrolytes, when they dissolve in water, they actually dissociate. The ions separate from each other and spread out through the solution evenly, which is why solutions are homogeneous mixtures. And if we try to conduct a charge through that, then it will readily conduct the charge because it gives the electrons in the electricity a place to jump from across the ions. And then ionic compounds are also not very good conductors of heat, but they are very good conductors of electricity. They can conduct electricity also in molten state. So if you can melt one into liquid form, it will also conduct electricity there. Now, some ions are what we call polyatomic ions, and this is a group of covalently bonded atoms, but there are not enough electrons to satisfy octet rule among themselves. So they're also going to gain or lose an electron or 2 or 3 to satisfy octet rule, which then makes it form into an ion because it has more electrons than it should normally. So if we look at nitrate as an example, using the Fvsbl method, to be full, all 4 atoms in that molecule need 8 electrons. So that's 32 total. But if we count up the number of valence available, nitrogen has 5, each oxygen has 6. So 6 times 3 is 18, plus 5 is 23. We can't make pairs out of an odd number of electrons. So when we go to draw the Lewis structure of the nitrogen, we end up with needing 4 bonds. And so nitrogen would be the middle atom, because it's the least electronegative, and the 4 bonds are dispersed to the 3 oxygens that surround the nitrogen, 1 for 2 of the oxygens and then 2 for another. And that's called a double bond, which is possible with some atoms. Some atoms can share multiple bonds. 2 is called a double bond and 3 is called a triple bond. And then when you go to put the electrons in pairs on the atoms that don't fill octet, you end up being short 1 because it was an odd number of valence available. So what happens is the nitrogen picks up an electron from something less electronegative than it and ionizes to form this nitrate ion, which is a -1 charge. So one of these lone electrons on one of these oxygens was actually donated by another atom. Nitrate is also a good way to demonstrate a property of covalent compounds called resonance, which is where you have a multiple bond on one atom and single bonds on others. Well, that multiple bond doesn't necessarily have to be in a particular place. It could be on any of these 3 oxygens, for example. So there would be multiple ways to draw the Lewis structure for this molecule. And that's what we mean by resonance. So the theory is that nitrate actually spends time in all three of these configurations. So what that means is the actual distribution of electrons is an average shown by all the different Lewis structures that are possible for that atom. All right, so we briefly talked about intermolecular forces when we were in the matter unit. And so intermolecular forces mean forces that occur between molecules. So between different molecules of a sample, and that allow them to, one, stay in a certain phase. So we saw in when we were transitioning from solid to liquid to gas that the IMFs had to be broken to get the element to phase change. This also affects certain properties of these compounds. And so we're looking at three principal IMFs: London dispersion forces, dipole-dipole interactions, and hydrogen bonding. London dispersion forces are going to be present with all covalent compounds. Right? These are very weak forces of attraction between the different molecules in a covalent compound sample. They only really become significant when the molecules are close together, which means when it's in solid state is when they really matter. The larger and heavier the atom is, the stronger the London dispersion force is going to be between those molecules. And what they're going to generally do is increase the boiling and melting point of a substance. So if we compare something that is showing LDFs versus something that is not, the one that has the LDFs is going to have a higher boiling and melting point. Because in order to boil or melt, you have to overcome the intermolecular force as well as give the element enough energy for the atoms to move apart. So if we kind of look at the halogen group, we can see that as the molar mass, which is the sum of the atomic masses of the element. So if I go to the periodic table and I look at the atomic mass and I add up the atomic mass for the atoms in this molecule, that's how I get this. If I look at this, as we go down the halogen group, the molar mass is increasing. The atomic radius is increasing. We already learned this. But if we look at their relative boiling and melting points, they're also increasing. And that is because the molecules here at the bottom of the group are experiencing stronger London dispersion forces compared to something at the top of the group. All right. So with dipole-dipole interactions and with hydrogen bonding, we have to understand molecular polarity. And that means that when you have molecules that hit that right amount of electronegativity difference, you will have a partial positive charge on the end of the molecule where the less electronegative element is, and a partial negative charge on the end of the molecule where the more electronegative element is, which is symbolized by this weird-looking S or O with a curlicue, whatever you want to call that. So using hydrogen chloride as an example, the hydrogen is not as electronegative as the chlorine. So the chlorine becomes an electron hog and pulls the shared pair of electrons that exist in this bond closer to it, making it the negative dipole. And then the hydrogen becomes the positive dipole. Well, we know positive and negative charges attract, so the negative end of one molecule and the positive end of another are going to attract together. And that's going to affect how the molecules arrange themselves. So you could see it end to end, or you could see it opposite each other so that they're stacked. So for the most part, those are going to be called dipole-dipole attractions, and that's where you have the opposite dipoles attracting to each other. Dipole-dipole attractions make it more likely that an element is going to be either liquid or solid at room temperature. And if we compare something that shows a dipole-dipole attraction to something that is similar in weight but only has London dispersion forces, then the dipole-dipole molecule will have a higher boiling and melting point. So, for example, if we look at hydrogen chloride and fluorine, molecular fluorine, both have 2 atoms. Hydrogen chloride's molecular weight is 36, fluorine's is 38. So they're very similar in molecular weight. But hydrogen chloride's boiling point is 188 Kelvin compared to fluorine's boiling point, which is 85 Kelvin. And that is because the hydrogen chloride is showing a dipole-dipole attraction, and fluorine is only showing London dispersion forces. Now, certain molecules, when hydrogen pairs with specific elements, oxygen, nitrogen, fluorine, you have this very large electronegativity difference, and so you see a much stronger dipole-dipole attraction between those kind of bonds, where hydrogen is going to have the positive dipole and the other element is going to have the negative dipole. Okay. So those dipoles are going to strongly attract to nearby molecules that have the same dipole, and we call that hydrogen bonding. Anything that hydrogen bonds has a much higher boiling and melting point compared to something that was just doing a dipole-dipole attraction, or something that was having a London dispersion force. And so, but it's specifically when hydrogen bonds with fluorine, oxygen, or nitrogen. And so if we look at water, for example, so with the water you have the oxygen and the hydrogen, and this is going to have a dipole moment, and then the negative oxygen is going to strongly attract to the positive hydrogens on a nearby water molecule, and you're going to get this hydrogen bonding. And so this hydrogen bonding is responsible for a lot of water's unique properties. Number one, the fact that when water freezes, it expands and is less dense than its liquid state. Because when you freeze, they can only lock themselves into this geometric pattern where you have these empty spaces, because the dipole moments are holding them there. And so it causes them to be spread out more versus anything else freezing, where the molecules are going to just compact up against one another. And then there's a lot of other unique things that water can do because it hydrogen bonds that we're going to explore when we talk about solutions later in the year. Okay. Another example of all of this is if we look at the boiling points of the group 15, 16, and 17 hydrides. All right, so if we look at ammonia and phosphorus trihydride and arsenic trihydride and antimony trihydride, if we look at their boiling points, so ammonia boils at somewhere around negative 25 degrees Celsius, and then phosphorus trihydride boils at a much lower temperature, and arsenic is lower, and antimony trihydride is a little bit higher. But compared with the rest of the group, nitrogen or ammonia has a much higher boiling point. Same thing with fluorine. Fluorine has a much higher boiling point compared to the other halogen hydrides, such as hydrogen chloride, hydrogen bromide, and hydrogen iodide. And then water has a much higher boiling point than any of the other pairs in group 16. And that is because these three are going to exhibit hydrogen bonding. These are probably, and some of these are going to show either London dispersion forces, or there may be dipole moments here. And then these are going to have dipole moments. And so, again, we can use what type of intermolecular force is present to guesstimate at the properties of those compounds versus compounds like it with different types of intermolecular forces.